So now let us invite our next speaker, who is Akanksha Gautam, and the speaker will present on holography with incoherent light. And the speaker is from the Lab of Information Photonics and Optical Metrology, Department of Physics, IIT Varanasi. Okay, so kindly start presenting.
Hello, am I audible, sir?
Yeah, yes. Please share your screen and please start your presentation.
Hello, everyone. I'm Akanksha Gautam, working under Dr. Rakesh Kumar Singh at IIT BHU, Varanasi, India. I want to firstly thank HMAM for giving me the opportunity to present my work. So the title of my work is Holography with Incoherent Light. So holography is a technique which records the whole information present in the light field, and later we can digitally reconstruct it. Okay, so digital holography basically uses the principle of interference of two coherent waves. So when the two, so which basically results in an interferogram, which we can record using a CCD or a CMOS, and later we can reconstruct the information about the amplitude and the phase by digitally processing the results. So basically, a coherent source is used to achieve the interference in the digital holography, but it suffers from the speckle noise and the edge effects, because due to the high coherence of the laser and the roughness of the object, the scattered light will be coherently superposed on the holographic plane, which results in the speckle noise, and hence the contrast and the resolution of the reconstructed image limits the application of the digital holography. So in that case, we can use the interference of the incoherent. In that case, we use the incoherent imaging systems like the broadband sources, like a light emitting diode, which are free from the speckle noise. So basically, the incoherent digital holograms are are basically obtained when the incoherent light is reflected or emitted from an object, and it interferes, so which basically results in an incoherent digital holograms. So there are many known methods of recording incoherent holograms, which are based on the principle of self-interference. So self-interference is basically all the points, all the source points are acting as as an independent scatterers, but they are spatially coherent. So what happens that that they can generate an interference pattern with the light coming from its mirror imaged point. So like that we can obtain the interference in the in case of incoherent light, and these techniques record the incoherent hologram in the form of intensity patterns. But there is also another way to record the incoherent holograms, which is based on the principle of two-point spatial coherence function. So in this poster, I am basically presenting an experimental approach to record incoherent object hologram as the two-point spatial coherence function using the Sagnac radial sharing interferometer. So so this technique basically derives its basic principle from the Van-Sitter-Janneke theorem, which basically says us that which connects the far field coherent function with the source's intensity distribution. As you can see from this figure 1, here I have shown an object letter 5, which is illuminated by a yellow light emitting diode LED source. Using a lens L, we can get the Fourier transform at this another plane, whose coordinates are represented by R1 and R2. So here the field ER is represented by this form, and finally the complex coherence function at the Fourier plane is given by the ensemble average of the field points at R1 and R2, that is E conjugate R1 and E R2. And on further processing the results, as all the points are acting as an independent scatterers, so they are delta correlated. So by using that relation, we can obtain equation 3 using this equation 1 and 2. So here you can see that finally the main result of my paper is that equation 3, which represents, as you can see, that inside this curly brackets it shows the Van-Sitter-Zernike theorem, which basically tells us that that the complex spatial coherence function, 2-point spatial coherence function, is nothing but the Fourier transform of the object intensity or spectral density, which is given by eta. It's Fourier transform. So now to reconstruct the object letter 5, we can back propagate, or we can just inverse Fourier, we can take the inverse Fourier transform of the coherence function, and hence we can obtain the object intensity distribution. So here I have shown my experimental technique. So as you can see from the figure, that I have divided it in basically 2 parts. So the first part basically does the Fourier transform of the object. Here this black dotted line shows the Fourier transform. So what happens is like as I have discussed in this principal part, that it will do the sequential scanning, like it requires a sequential scanning, so which is quite impractical to do. So what we do is we uses a interferometer. Here I'm using the Sagnac radial sharing common path interferometer to get the object information simultaneously, the whole object information, so that I don't need to sequentially scan the whole object. So so firstly the this letter 5 is Fourier transformed, and here we get the interferogram, that, or we can say the spatial coherence function. And now to measure this spatial coherence function, I have designed a common path square Sagnac radial sharing interferometer. So light is divided into 2 orthogonal polarization state X and Y respectively, by using this polarization beam splitter. And then I have used the combination of 2 lenses, L2 and L3. So what happens that they are of unequal focal lengths. So they basically provide in plane radial shear between the 2 counter propagating beams. So that so here a magnification and a demagnification factor alpha and alpha inverse comes. So basically that alpha is given by f3 by f2, and that alpha inverse is given by f2 by f3. So so the 2 wavefronts, one gets magnified and the other gets demagnified. And finally at the camera or CMOS plane, we will get the interference pattern. And this as these 2 beams are orthogonally polarized, so to achieve that interference, we are using a quarter wave plate, a combination of quarter wave plate and a polarizer. Here I have used that lens L4 just to image this plane, because the image is not coming inside my whole camera. So just to image it, I have used this lens L4, and then finally I have used a quarter wave plate and polarizer to act as a phase shifter. So this quarter wave plate is kept at 45 degree from its fast axis, and it will basically changes the 2 orthogonal polarization, linear polarization states X and Y into RCP and LCP, that is right circular polarization state and left circular polarization state respectively. And then that polarizer P2 is kept which will provide the interference as well as also give the phase shifting. So the 5 interferograms with the phase shift 0, pi by 2, pi, 3 pi by 2 and 2 pi like this are recorded, and then finally we will reconstruct, we have digitally reconstructed the fringe visibility and the corresponding phase using these 5 recorded interferograms by using the 5 phase shifting algorithm. And then finally, I have reconstructed my object intensity distribution by inverse Fourier transforming the obtained complex coherence function. So the complex coherence function is built using this fringe visibility and this fringe phase. Like if fringe visibility is given by gamma and phase is as phi, then the complex coherence function is given by gamma exponential iota phi. So like that, I have digitally reconstructed my my 2-point spatial coherence function, and finally by inverse Fourier transforming it, I have obtained my object information. Here I have shown this image shown the letter 5, and then so finally I conclude my poster that I have presented an experimental approach based on the sharing. So the object information is recorded in the form of 2-point spatial coherence function, which derives its basic principle from the Vansittart-Janneke theorem. And later I have analyzed this complex spatial coherence function using the Segnick radial sharing interferometer with the 5-phase shifting algorithm. And then I have retrieved the object information computationally by doing the inverse Fourier transform. Here I have presented some references. So thank you all. Like this, I would like to conclude my talk.
Yeah, thank you very much, Akanksha, for your very nice presentation. So I think it looks, I mean, the technique for imaging with the incoherent light is kind of, it looks familiar with our previous studies in Finch and
Yes,
Fish.
sir.
Yeah, so it is very
Yes,
nice
sir, yes.
to see this configuration. And also you have smartly put these two lenses, because I was wondering, I mean, when you had this arrangement, whether the beam sizes would be
Yes.
the same, but
Yeah.
then I understood that you have these two lenses at the appropriate places, so you retain the beam sizes and you have, I think, better fringe visibility. And when you presented, you said that you took 5 phase shifts. So why you need 5
Yes,
phase
sir,
shifts? 5 phase shifts.
So actually, with the 3 and 4 phase shifting, also we will able to reconstruct the latter. But there is a conjugate image coming in that 3 phase shifting. So I have used the 5 phase shifting to just remove the effect of that conjugate image.
Okay, and also when seeing your holograms and this results, so why your result
Yes.
look noisier? So
Yes, sir. So actually here is this LED, no? So its effect is also coming here. Like this, you can see that LED is of this shape, as I have like shown that this shape. So there is dark spots in that LED. So that is also like I think that is also overlapping with my that object like object information. So because of that, in that the whole letter is not like that
okay,
much.
yeah, I understand. Yes. So have you
The
tried,
dark
I
side.
mean, 3D imaging with this?
Yes, I am doing simulations, and I'm planning to do 3D as well.
Okay, nice. I think it will be a very good work if you succeed in making 3Ds. Okay,
Thank you
and
so much.
okay, so there is a question from Andre.
Okay.
Oh, hi. So I have a
Hello.
question about your experiment and results. So I see that you used
Okay.
like this square Sagnac interferometer
Interferometer.
configuration. Yes.
Yes, sir.
But what I was wondering is if you've ever used something like Michelson interferometer there. If you could tell me a bit like what would be the advantage of using Sagnac in this scenario? Would there be any sort of major difference? You know, if you have used any other type
Yes,
of
sir.
yeah. Yeah.
So in yes, so in SAGNEC, I think it's easy for me to do. In Michelson, like so you have said Michelson or Maxenter.
No, I said Michelson, not Max Zender.
Michelson.
Yeah.
Okay, Michelson interferometer. So I haven't. Yes, in Michelson, like you want to give the sharing between the two beams. So, like I have tried with Maxender and Sagnac, because in that case, like the two like here I have used to counter propagating beams, and in these two beams I am giving the phase shifting. But in case of Michelson, if I see, then I have to put two lenses there, and then I think I need more lenses in case of Michelson interferometer. I think in the both paths I have to give, because this principle is based on sharing between the two beams. So in that case, I think in that case I need more lenses to do the experiment. In both paths, I have to use the combination of the lenses, I think, in Michelson case.
So how
So
about
this
using a
technique,
concave mirror instead of using lens? In Michelson, you can replace the plane mirror with a concave mirror, right? So then will it be useful?
concave mirror.
then
Oh,
you get light focused, and then you get a similar effect.
okay.
I'm not sure whether you can reproduce it, but this is a very good question, I think.
Okay. Yes, as I will just look into it and I will try if I get any results, or like I will try the experiment and then I will let you know. That,
Okay, so Andre, so you have any further questions?
No, not at the moment. That's the thing I want to ask about the
Okay.
and
optical.
one more thing, that in that case there is no temporal coherence effect because it's a common path interferometer. So I just want the sharing, like the spatial coherence I want to measure. So as both the beams are traveling the same path, so it's easy to obtain the spatial coherence. Like to deal with this segment is a little more easier, I guess. I
Yeah,
will
you're
see
right.
about that, Michael. Yeah,
Yes.
yeah.
Okay, so let us see if there are any other questions or hands up. No hands up. And chat window again. No. So if there are no further questions, then let us thank the speaker again. So thank you very much for the nice presentation.